Yeah, so everything okay? Let me first introduce myself. I've been a software developer for around 6 or 7 years. 3 of those I'm building stuff with Erlang. So yeah, that's everything you should know about me. Yeah, let's start. Yeah, so this was Mahler's Fifth Symphony. So you're probably asking yourself, what does this have to do with Erlang? And quite a lot. Music is actually a parallel problem. And it's also fault-tolerant problem, because if one of those 16 instruments stops playing, they won't all stop playing. Just one of them, and 15 will still continue. So an orchestra is error resilient. So can you imagine sequential music? You come and you come to a show, and the first thing is that the first trumpet starts playing, and then the second, and then the first violin, and the second, and the third, and the fourth, and so on. So what I'm trying actually to say is that solving a parallel problem with a sequential language is hard, and you hit accidental complexity. So what does accidental complexity mean? For example, if you try to solve it with C++, you have abstractions for concurrent programming, mutexes, semaphores, signals, and so on. And this is really hard. So the harder the parallel problem is, the more complexity you get. And then you decide, okay, let's go a level higher, and you try with Java or C#. But you have the same abstractions. You hit the same level of complexity, no matter the language. So if you only have those 3, or I think it's in Ruby it's the same. If you have only those languages, you have to conclude that parallel programming is extremely hard. But just remember one thing. What do all those languages have in common in case of parallel programming? Shared memory. So I'm trying to convince you that shared memory is actually the root of all evil. And okay, Robert Werding, that I've met in London on a conference, and I told him also about ActorDB and was extremely thrilled about it. I'm going to talk about ActorDB later. Robert Werding always says that Erlang is not an academic tool, but it was made to solve a specific problem. And the problem was the large telecommunication systems. And those systems needed high productivity, so they had to be abstract. If something in the systems goes wrong, they have to be able to restart and repair itself. The systems could be distributed over large clusters, and many of them. And the system must be able to handle a very, very large number of concurrent operations. And all upgrades and patches and so on, software maintenance should be done without stopping the system. And if you think about those properties, you can conclude that this actually involves all software, all software services, servers, and so on. It's not only for telcos. So the consequence of solving this problem was an implementation of actor model. I won't go to the details of actor model. The only thing that I'm going to say is that it's a mathematical model for concurrent computations, and it takes a different approach about concurrency and should avoid or should solve the problems caused by threading and locking. The one and only entity in actor model is an actor, and this actor has a specific behavior. It has a mailbox, and it sends and receives messages. And if one actor wants something from another actor, he has to send him a message and just request him for the information. So Erlang actors are part of the language itself. You can't imagine Erlang without actors. So implementation in Erlang for actor is a process. So everything you do is a process. So something now about the future. As you can see, all your machines have 4 or 8 or 12 or 16 cores. And it won't be long that we'll have machines with 1,000 or more cores on a single chip. And at that moment, the world for the developer is going to be completely different. The developer that would program on that kind of chip would know nothing about the world that he's been brought to. He doesn't know what the load is, how many cores there are. It doesn't know what the priorities between the cores are. So the next level code would have to be written in a level of abstraction that will be adapted at runtime. And it's not unusual if Erlang apps have, for example, 100,000 or even more processes. And each process has its own small task that it solves in sequentially. So how can you imagine processes in a system? You can imagine like an ant colony that those ants communicate with themselves or with others just by sending messages here and there. But if you say a process, then you think about operating system processes. But in Erlang, those are not operating system processes, but are the processes in a virtual machine. So spawning 10,000 new processes on a single machine takes less than 10 microseconds per process. So they are extremely fast, they are dynamic, they have a mailbox, and so yeah, for example, garbage collector runs per process. But Erlang applications are designed architecturally quite different than any others. You have supervision trees, and those supervision trees are meant to watch over processes. So a supervisor has, I don't know, 100 or 150 or 200, doesn't matter how many processes. And his work is that he watches for them. As soon as one of the processes dies that he supervises, he has to, as a supervisor, he has to decide what to do. You have many options. One of them, 2 of them are, for example, you can restart all the processes or just the one process that died. The thing is that we always restart the process from a state that we know that it runs. So from a clean state. What does this give us? We can always program for the correct case. Because processes are that much cheap that you can let them die. Because the supervisor will just will wake him up again from a clean state. So no defensive programming. So what do we achieve with these design patterns? Robustness and fault tolerance. So if you want to make really big systems, you have to isolate stuff. So you have to isolate processes from each other, so that you don't have error propagation in a way that it crashes your whole application or a system. So if you want to build fault-tolerant systems, you just need to plan for the failure. And you need to know what to do in case if something fails. So that's why I'm stating that building fault-tolerant systems with shared memory is impossible. So as you can imagine, I think you're all Ruby programmers, what does happen when a thread starts doing that isolated piece of code and it dies in the middle and it leaves memory corrupt? What will happen when the next thread comes in? It won't solve anything. It will die again. So this is actually quite bad. You can't have fault-tolerant systems with that kind of design. I mentioned also patching and upgrading software as it runs. So the next feature by design of Erlang is hot code loading. So applications are made of modules, and in modules there are functions. And you can have two versions of the same model, same model with the same name, with different content in memory. And you can have, you can send that process a message, and it will start using the next model that was, the fresh model that was loaded into the memory. And this is not this is not the thing only for systems in production, but it also shortens the development cycle. Yeah, so multi-threading and multi-processing. Okay, so I'm going to be short on the syntax because lots of people say that it's hard, and it's okay. It's different. It's not hard. We have three functions with pattern matching in the heads. This is actually quite powerful. It is also in several different languages, not only Erlang. But the most useful thing is when you try to implement TCP protocols. So in C, you would have to read the stream and then parse the stream bit by bit and then decide what to do. So in this case, you get a stream, TCP stream into the process, and the process will send it through all the functions and find a pattern that matches and execute that function. So for example, the difference between the first one and the second is just by the first bit, and the API key is actually a variable that already holds proto-buffers, and they're ready to be decoded. Yeah. So the next thing that's different is single assignment. When you start programming in Erlang, that's something quite unusual, but come to think about it, single assignments is just like algebra. You don't change variables in algebra. So you can't have statements like x equals x plus 1 in Erlang. Seems weird at the beginning, but you then find out that that's the right way, and the quantity of bugs is very, very minimized. So every assignment is actually a pattern matching. So everything on the right wants to fit into the thing that's on the left. That's the easiest way to explain it. So we have also anonymous functions, because Erlang is dynamically typed. So you can have anonymous functions. They're the same as normal functions. The only thing that's different is that they can't call themselves. So, okay, we also have if and case statements. If statement isn't much different than any other language. Then you have case statements. Case statements are actually switches on steroids that pattern match in every case. So this is really cool. The next thing that's pretty hard is recursion. Yeah, so you start programming and you're looking for loops, and there aren't any. So you have two options how to write recursion. One is the wrong way, and one is the good way. So tail recursive functions, you have to watch out that the last call in a function, in a recursive function, is a function, so that the compiler can make some great optimizations, and this way you won't have a stack overflow. You probably all know about it. So okay, this is it. So the core of Erlang, it's spawning processes. So the spawn function makes a new process, and the respond function now runs in that new process, and it waits for a message to be received. So yeah, that PID, it's a process identifier that the spawn function returns, and we are sending it data 12 and 14, and the last case on the receive, and we'll just accept it. So who's using Erlang? Well, the funny thing is that almost all large companies, somewhere in the company, they have Erlang. The thing is that they don't talk about it because it works. So 40% of all global traffic over 3G is over Erlang, and 60% over 4G is over Erlang. So all the switches are written in Erlang. So yeah, and also WhatsApp uses Erlang. They have, I don't know, 500 million users, and they send around 40 billion messages per day, and it's all made in Erlang. So I mentioned Erlang, Demonware, core online services of Call of Duty. Everything for multiplayer goes through Erlang, and also Python, I think. CouchDB is in CERN. It has, I don't know, tons of petabytes of data that the Large Hadron Collider produces, and it's all stored in CouchDB. Okay, let's go to the next topic. That's ActorDB. So I didn't mention that I work at Biocoda. That's a relatively small company in Maribor. Around 10 programmers, 4 or 5 of us are Erlang programmers, and we decided to build our own database. I'm still convinced that it was an insane thing to do, but we had a great idea and we just couldn't forget it. So we decided to build it just because it fitted our product the best way imagined. So we started out working on a project called Emit Cloud, and Emit Cloud is basically a private Dropbox that you install on your servers, on your server in your home, or for example, a telco can install it on large clusters, have millions of users, and offer the service to the users. So the data that Emit Cloud produces are basically files, folders, and events. So files and folders are building a tree, a hierarchy, and events are just sequential move, new, delete, upload, and so on. So everything that the user does belongs only to him. And we first had it a mixture of databases, but the SQL databases, the relational databases offer you some great things that you can filter stuff, you can group them, and so on and so on. So the question I'm asking, why would you have a SQL database where you would have to put everything in a single database? So we decided, okay, what if we can make a database that will be relational, and every single user would have its own database? So ActorDB was born. So when we solved the problem, we actually could keep the relational database and have concurrency for each of the user that's using our Emit Cloud. So what does ActorDB actually mean? It means splitting your data set into small independent chunks. It was inspired by the actor model that I mentioned earlier. But here, an actor is actually a SQLite database that lives in a cluster. And that cluster could be just 1, 3, or 5 servers. So as you can see, there's a lot of talking between the servers, in between the cluster, between the clusters, and so on. And if you understood anything that I mentioned earlier about Erlang, you have to know that now that Erlang is good at message passing and talking between servers and talking between processes, and so on. Yeah. So remember that each ActorDB is completely isolated. Every actor is a complete, separate SQLite instance. And this is not where the scalability of ActorDB comes. Okay, this is just the syntax. So we just added a couple of stuff that we needed to the normal SQL language. So the query starts with an actor keyword, and then you select the type of actor that you want. You can have many actors, many different actors with different schemas. And then you select the ID of the actor. So for example, this would be Emit Cloud user with an ID 1013. And the create flag is there just for the sake. If we don't, if the actor doesn't exist, then we create it. And the select from file is just regular MySQL. You can also have queries over multiple actors or all of them. Um, um, or just for the last example shows that you can just print all the actors that already exist. But you can have two types of actors. This is a regular actor with its own SQLite database. The next one, the second one, is a key value database. So to explain it, yeah. So you have a table, and you have 10 or 15 servers, and that table will get sharded all over the cluster, all over all servers. So once you start using it, it will create new shards, and all the shards will be distributed all over the cluster. The syntax is a bit verbose, but it's quite powerful. So the counters here are a key value namespace. You can have multiple namespaces with different schemas. You can also have tables that are connected with primary keys with each other. Just the first table has to be named actor, and the first two fields have to be ID and hash. All after that, it's all up to you. So yeah, that's it from me. Yeah, questions.
So these key value stories then actually stored in SQLite as well?
Yeah. Just the tables are sharded.
Oh.
Yeah.
How do you actually implement the SQLite databases? Did you just spawn a database on request, or did you re-implement them? Or?
No. The engine is the same. The only thing is that if an actor lives in 1, 3, or 5 servers in a cluster, and the database or the actors get distributed all over the cluster with algorithm called Murmur, and it just divides the 32-bit space into small spaces, and it sends actors to the servers. And you have in a cluster of 5, for example, you have a master actor that implements all the writes and the reads, and 4 of them that are slaves that are just replicating itself in the cluster. But the thing that we do is just appending wall logs to the for other replicated instances. Yeah. Anything else? Who else? Yeah, we use it in all our products. We didn't invest into make it more popular because it takes a little bit more time data can be expensive, and you really have to be big to afford a mistake on the data part, and so this is our next goal, to make it more popular. Yeah.
Okay, any more questions?
How do you use and write with
Hot code loading.
Yeah.
So you have 2 options for calling a function inside a module. So inside of a module, all functions are public. And if you want to load the new module, you can use a function called apply that takes 3 arguments, a module, function, and arguments, and that will ensure you that the new code will be loaded. And the second one is just to call it with module name and function, and this will always be executed on a new in a new module. Dependencies? What kind of You don't have dependencies in Erlang. Because, you know, everything in Erlang is a process that contains functions. And you don't have hierarchy between modules. Yeah. One tweet was, I had on the bottom right, how was it? Yeah, the discipline, the tools. Yeah. So, thank you.